Now diazonium salts. Diazonium salts. Diazonium salts having the general formula Rn2 plus X minus. All of you know what is R? R stands for, in fact it is aryl group, because aliphatic diazonium salts are unstable even at a low temperature. That's why it is aryl. It is aryl diazonium salt. R stands for, in fact it should be Arn2 plus Cl minus or X minus. X stands for chloride, bromide, HSO4 minus, BF4 minus, etc. So benzene diazonium chloride, benzene diazonium bromide, benzene diazonium hydrogen sulfate, benzene diazonium tetrafluoroborate, like that. So that is diazonium salt, general formula. General formula and the characteristics of diazonium salt. All these points already learned. Primary aliphatic amine forms highly unstable alkyl diazonium salts. They are unstable, they are not stable even at a low temperature. While at a low temperature 0 to 5 degrees Celsius, aromatic diazonium salts are stable. They can be isolated. Primary aromatic amine form arene diazonium salt, which are stable for a short time. That's why we don't prepare diazonium salt and store. We prepare diazonium salt in situ. Whenever it is required, we prepare and use it straight away. At a low temperature, stability of arene diazonium salt is due to resonance. It is due to resonance. You can see the resonance character due to the electron donating effect plus R resonance shown by benzene ring, or minus R effect shown by diazonium group. Diazonium group act as a minus R effect group. So it is withdrawing electron density from the ring and hence it is trying to stabilize, which otherwise it is quite unstable. All diazonium salts are unstable because why all diazonium salts are unstable? Rn2x minus. Why this is unstable? Because N2 is highly stable. Why should N2 stay back there? It can easily escape. No, once it get an opportunity, it is immediately escaping as N2 gas. That is the point. While in aromatic compound, it can be stabilized to certain extent by resonance. And this is what the preparation of diazonium salt, all of you know, diazotization. Aniline treated with NaNO2HCl will produce HNO2. HNO2 interact with aniline and you get benzene diazonium salt, detailed mechanism explained in the classes, and it's given as a note how the diazotization reaction take place, and you get diazonium salt explained in detail and is given as the notes. Please review, as the mechanism is not intended in the text. This is diazotization. When you mix NaNO2HCl, you are actually taking nitrous acid. Nitrous acid is unstable and is prepared in situ. And this, when treated with aliphatic primary amine, that is the so-called aniline. This is aniline. You get benzene diazonium chloride. Diazotization. Already learned when we were learning Sandmeyer's reaction and all. And now the benzene diazonium chloride, a talk on its properties. Benzene diazonium chloride is a colorless crystalline solid. Readily soluble in water, stable in cold condition, but react with water when warmed, and it is immediately hydrolyzed to get OH product, alcohol phenol product. It decomposes easily even in dry state. while benzene disonium fluoroborate is water insoluble and stable at room temperature. That is C6H5N2 plus BF4 minus. That is stable at a room temperature and is water insoluble. And there are two kind of reactions given by disonium salts involving displacement of nitrogen. And very famous reaction is Sandmeyer's reaction. And this is what Sandmeyer's reaction, a combination 3 reactions. Benzene disonium chloride treated with the cuprous chloride HCl, you get chlorobenzene. Cuprous bromide HBr, you get bromobenzene. And cuprous cyanide KCN, you get cyanobenzene or benzonitride. Right? A detailed mechanism again for Sandmeyer's reaction. Detailed mechanism explained and the note is given. Right? Regarding how that benzene disonium chloride interacting with cuprous halide and you get chlorobenzene, bromobenzene, etc. Sandmeyer's reaction. A detailed script on the reaction mechanism is given in the notes. Please review as a competitive aspect. Not required for the board exams. That is about the Sandmeyer's reaction and it involves nitrogen gas. And alternatively, there is another technique. Hope you remember, also discussed during Sandmeyer's reaction earlier. That is called Getterman reaction. Getterman reaction, a modified version of Sandmeyer's reaction, where benzene disonium chloride treated with the copper powder and HCl or copper powder and HBr giving chlorobenzene, bromobenzene, called a Getterman reaction. So Sandmeyer's reaction and a modified version of Sandmeyer's reaction called a Getterman reaction. Anyway, the yield is greater in Sandmeyer's reaction, already taught in the class, right? And this is preparation of iodobenzene, benzene disonium salt treated with the Ki, you get iodobenzene, direct preparation. And preparation of fluorobenzene, hope you remember, what is the name of the reaction? Taught in the class, exactly, Bal-Schiemann reaction. Bal-Schiemann reaction. Preparation of fluorobenzene, benzene disonium chloride treated with HBF4, you get benzene disonium fluoroborate, which upon heating you get fluorobenzene BF3 and expelling nitrogen gas. Bal-Schiemann reaction. All these reactions explained when we were learning Sandmeyer's reaction earlier in the previous chapter. Right? Now, one of the very important reaction is replacement by hydrogen. How benzene disonium salt is reduced to benzene. How that can be done? That is two important reaction of benzene disonium chloride treated for reduction. This is the reaction. Benzene disonium chloride treated with hypophosphorus acid, H3PO2. What is the name? Hypophosphorus acid. It's a good reducing agent. Phosphinic acid. When treated, this is reduced to benzene and itself this is oxidized to phosphorus acid. So S3PO2 oxidized to S3PO3 while this is reduced to benzene. In fact, what happened ultimately is N2 group replaced with a hydrogen. Isn't it? Fine. Very important reaction. And a similar reaction, same thing. This is oxidized. This is reduced. This is reduced to benzene while this is oxidized to ethanol. Here we make use of ethanol. So either by using S3PO2 or by using ethanol, we can reduce benzene disonium salt. Benzene disonium salt is converted to benzene and ethanol oxidized to ethanol. S3PO2 oxidized to S3PO3. Right. So these two are very important reaction. Don't forget, as it is coming once in a while for the exam. So exactly we don't know which exam it is going to be. So definitely please ensure you have gone through that reaction and equip yourself to answer when come for the exam. Next, another reaction. This is already learned in the preparation of phenol. Benzene diazonium chloride warmed with water. You get a phenol. Preparation of phenol already discussed during the preparation of phenols. Right? While there is another reaction, substitution by nitro group. Substitution by nitro group. Benzene diazonium chloride treated with a HBF4, where we convert into benzene diazonium fluoroborate. Benzene diazonium fluoroborate, and that treated with NaNO2 and copper powder. That heated with NaNO2 and copper powder, where this group is replaced by NO2. You get a nitrobenzene. Nitrobenzene. Right? That is another separate reaction. So this much reaction for the replacement of diazo group. Sandmeyer's reaction, Getterman reaction, replacement with iodine, Balshiman reaction, reduction using S3PO2 and ethanol, then converting to phenol, and now this reaction. In fact, diazonium salts are popular known for another kind of reaction. All of you know, it is coupling reaction, diazo coupling reaction. Diazo coupling reaction. This is what the coupling reaction is. Benzene diazonium chloride. Benzene diazonium chloride treated with phenol. Benzene diazonium chloride treated with phenol. Two examples given, and there will be electrophilic aromatic substitution reaction. This act as electrophile. This act as electrophile. This in fact act as electrophile, and it is electrophilic aromatic substitution reaction. You get a azo coupled product, para-hydroxy azobenzene. Para-hydroxy azobenzene, an orange colored dye, and such compounds are called azo dyes. Azo dyes. This is the color causing group called chromophore. The color chromophore, the color causing group, NN group is acting as color causing group called chromophore, while this is called oxochrome. Oxochrome, color intensifying group. And this is coupling reaction, where you can see the two benzene rings are coupled like this with the NN linkage. That is what happening. That is azo coupling. We have another example, benzene diazonium chloride treated with aniline. Treated with aniline. There is electrophilic aromatic substitution reaction. You get para-aminoazobenzene. Para-aminoazobenzene. Here it is an orange dye, and here it is a yellow dye. Right? Again an azo dye. This is one of the most important reactions given by diazonium salt, azo coupling reaction. And such a reaction and a product maybe all of you are familiar with. And of course, notes are given. Hope you remember, where we take such an example. A diazonium salt formed by sodium salt of benzene sulfonic acid, sulfonilic acid treated for diazotization. You get this molecule, sulfonilic acid. Do you remember sulfonilic acid? This is sulfonilic acid. This is sulfonilic acid. Sulfonilic acid treated with NaNO2 HCl at a low temperature, you will get this diazonium salt. And imagine this diazonium salt is treated with N-dimethyl aniline. N-dimethyl aniline. This is N-dimethyl aniline. N-dimethyl aniline treated with the diazonium salt of sulfonilic acid. This is sulfonilic acid. You get an azo coupling product which seems to be like this. This is an azo coupling product obtained in that example, which is very popular. Quite frequently all of you are using in the laboratory and used in the laboratory for acid base titration as a indicator. The one so called exactly methyl orange. Methyl orange. Methyl orange is a azo dye obtained by coupling reaction like this, right? And there actually we come to an end of the chapter amines. The chapter amines comes to an end at that point. Let us have a quick review the regarding important points. We started from the structural details of amines, primary, secondary, tertiary amine, nomenclature, isomerism, etc. Preparation of amines, reduction of nitro compounds, Hoffmann's ammonolysis reaction, various related reactions, reduction of nitriles, reduction of amides, Gabriel reaction, Hoffmann's bromamide reaction, physical properties, chemical properties, special emphasis to basic nature of amines, a detailed talk on aliphatic aromatic amines and substituted aromatic amines, ortho effect, methylamines, ethylamines, vapor phase, aqueous medium, etc. and various reactions, electrophilic aromatic substitutions on aniline, controlled electrophilic reaction, controlled bromination, controlled nitration by acylation, etc. Special talk on nitration of aniline where meta product obtained 47%. Then sulfonilic acid formation, Switrion formation. Then carbylamine reaction, acylation, benzoylation, Schotten-Baumann reaction, Carbylamine test, reaction with the nitrous acid, primary, secondary, tertiary, aliphatic aromatic amines, Hinsberg test, right? And diazonium salt reaction, San-Meyer's reaction, Balchuman reaction, reduction to benzene diazonium salt reduced using H3PO2 and ethanol, various reaction, and finally coupling reaction. These are the main points from the last recognized organic chapter from the 12th standard topic. There we come to a conclusion on the topic. We will meet with another chapter in another class. Till then, bye, take care, see you.